Welcome to this lecture on hydrostatic pressure forces and the center of pressure. In this lecture, we'll talk about how one finds the resultant force and the resultant force location on a surface that's submerged in some sort of fluid. So if you take a look at your screen here, you'll see, for example, the Glen Canyon Dam located in Arizona. And it's actually, I think, the second biggest dam in the United States after the Hoover Dam. You can see all this water that's been backed up behind it. Obviously, there are enormous pressure forces acting on this dam. And of course, as engineers, we have to be able to predict what those loads are going to be so we can design for them. So we want to make sure that we understand how to calculate the pressure forces resulting from hydrostatics. So that's what we're going to do in today's lecture. And we'll also calculate the center of pressure, which is where that resultant force would act. Also, right, so let's get into it. And just to start with, as a reminder, when we first introduced the idea of pressure, we had the following picture. We had some little surface area, or some little area called dA, which had some magnitude and a normal unit vector associated with it. So we'll draw the normal vector that way. And the pressure force acting on that little bit of surface would act inward. And we'll write it as dF, P, equals P times minus dA. Right, so it's the pressure acting on that little bit of area, and it acts inward. So it's the pressure times the area, so P times dA. We're doing things in little bits here, so we can add them all together at the end. And the pressure force acts inward, so that's where the minus comes from. And the idea here is if we wanted to get the total pressure force on some surface, we add up all the little bits of pressure force over the whole surface area. And that allows us to take into account any changes in the surface orientation or variations in pressure. So if the area, this is the area A, I'm just drawing it from the side. If the orientation of the surface changes from point to point, so here you can see the n hat changes orientation. So if the orientation changes and if the pressure changes over the surface, we wouldn't have a well-defined orientation or well-defined pressure over the whole area, right? It changes from point to point. So when we do it in terms of little bits, then we're okay. So over that little area dA, with that normal vector, the normal vector is well-defined for that little area. So that's not a problem. And the pressure is well-defined over that little area. So we can easily calculate the little bit of pressure force on that small area, and then we would just do it up over all the little bits of area over the whole surface, and that's how we would get the net pressure force acting on it. So that's exactly the idea that we're going to do in the examples that I'll cover here in this lecture. So what we're going to look at is just a very simple example. We've got a sort of an aquarium here, just a kind of a rectangular volume. We have a coordinate system down here in the back left corner, x, y, and z. Y is pointing upward. Dimensions L in the x direction, W in the z direction, H in the y direction. Gravity is pointing downward. We're going to say it's completely filled with a liquid. So the free surface is right at the top at position H. And what I want to do first, we'll just start with something very simple. Let's calculate the net pressure force acting on the bottom surface of this aquarium. Okay? So to do that, let's start first with a kind of very intuitive way. We know pressure times area is equal to a force. Well, on the bottom, the pressure is well defined. Right, the pressure force acting on the bottom, let me draw, so the pressure force acting on the bottom, it would be nice and uniform because the elevation isn't changing. And that pressure force in terms of the gauge pressure, or the pressure I should say, in terms of gauge pressure will be rho GH. Rho GH because we're doing gauge pressure, so let's not worry about atmospheric pressure. And then we're at distance h from the free surface, so the pressure at the bottom will be rho GH. And it's a uniform pressure over the entire bottom because it's all at the same elevation, just all the same depth h from the free surface. Also, the orientation of that surface is uniform over the whole bottom as well. It's all the unit normal vectors are pointing upward. So let me draw that in red. You can see the unit normal vector here is pointing upward. There's n hat pointing upward. It's the same n hat pointing upward here. Right, so we could simply, so in this particular case, the pressure and the orientation are well defined over the whole surface. So we could simply find the pressure force on the bottom will simply be the pressure there, rho GH, times the area, which would be just L times W, and it's going to act, actually let me change the area. Remember, the pressure is the pressure force is pressure times minus dA, so it'll be times a minus L times W with the normal vector pointing in the j hat direction. So this is our pressure, and this is our area. And it's actually an area vector, right? And then the minus sign, I should put in the minus sign here as well, just to make it less confusing. There you go. So that's the pressure on the bottom. Let me rewrite it one other way here. So it'll be minus, put the minus with the j hat. So that's our pressure force on the bottom. No big surprise. You could probably figure this out right away. And if you look at that equation, what it is actually we have a density times the volume of the liquid in the aquarium. So that gives us the mass of the liquid in the aquarium times G. That gives us the weight. So the bottom is supporting the weight of all the liquid sitting above it. Makes physical sense. Now let me rework this problem using the integration approach. Okay, so what I'm going to do, let me redraw the area on the bottom here, just looking at it from above. So here's our W. Here's our L. And let me put the coordinate system in there as well. So this would be Z. This would be X. So what I'm going to do is I'm going to look at a small area here. Let's call this distance. This is dz because it's a small displacement in the z direction. And this distance is dx because it's a small displacement in the x direction. So my little area there is going to be dx times dz pointing in the j hat direction. It's pointing upward, out of the page. So it's in the positive y direction, which is out of the page. Okay, so then our little bit of pressure force on that area is going to be P times minus dA. Well, the pressure we know already from the first part of the problem. The pressure on that little area is going to be rho GH because it's at the very bottom of the tank. So it'll be rho GH times a minus, we just said the area was dx times dz in the j hat direction. So that's our little bit of area, and then to get the full pressure force over the bottom, we're going to integrate over the whole area. Now the integral here, we'll have to integrate in the x direction and the y direction. I'm sorry, the x direction and the z direction, I should say. So we'll go from z goes from 0 to w, and x goes from 0 to L. Okay, well the rho, the g, the h, and the j hat are all constants, so we can pull them outside the integral. And then that integral, the double integral, is very easy to solve. The first one over dx, that's just going to be L, and the one over z is just going to be W. So what we'll get in the end is rho g h times L times W times minus j hat. So we get the exact same result we'd calculated before, right? So here's what we got just from the very beginning of doing this. This is what we get now. Exactly the same result. The integration approach for the bottom part of the tank isn't really necessary because everything's uniform and we don't really have to go through the integral. But I just wanted to do it just to show you that it works. Okay. Now let's look at the side of the aquarium. This one's a little more complicated. So let me redraw a picture of the side. So we have, here's the side wall. Remember, this is our free surface here. And let me put in, and here's the bottom. Let me put in my coordinate system. So here is the y direction. Here is the x direction. And let me sketch in what the pressure profile looks like against the wall. Pressure profile is going to look something like this. Remember, the pressure increases linearly with depth. And the pressure at the very bottom is going to be rho GH because that's, it's at the very bottom of the tank. Remember, this distance is h. So the pressure at the very bottom is rho GH. The pressure increases linearly with depth for this incompressible fluid. And so the pressure at the bottom is rho GH. Now here, when we think about pressure times the area gives me the pressure force, what pressure do I use? It's not clear because the pressure varies. Do I use the average pressure? Do I use the maximum pressure? Do I use 1/3 the maximum pressure? It's just not clear. Okay, so we don't have a well-defined pressure. So in a case like this, we really should be using the integration approach because over a small area, the pressure and orientation are well defined. Over the large area, the pressure is not well defined. So what we'll do is we'll zoom in on some little piece of the surface here, right there. In that area, let me actually put the dimension. This direction is a little bit of displacement in the y direction. So that area will be dy. And we could also do a small displacement in the z direction. So that's in and out of the page. So we could do another little kind of square, just like what we did up here. We could do a square, but now it would be a dy times a dz. We could do it that way. There's another way we could do it. Remember, what we want to do is choose an area over which the orientation and pressure are well defined. So another area we could choose would actually be a strip of area. Let me show that in a picture here. So we could, let me draw the sidewall in more of a perspective drawing. And we'll put in, again, the coordinate system. So here's y, here's x, here's z. So one area we could choose might be a little area like this, where this is, again, dy, and this distance would be dz. So we could do that kind of area because the orientation and pressure are well defined over that. Or another area, and the one that I'll use, will be a strip that looks like this, where this is dy, and this distance, of course, now is w. So we could use that area or the little one. Either one, because again, the orientation and pressure are well defined on those areas. The strip, the pressure is well defined because remember, the pressure only varies with the y direction. So if I choose a strip that's the same elevation in the y direction, the pressure will remain constant over that. So in this case, my little bit of area as a strip will be dy times w with the normal vector pointing inward, which would be in the I hat direction. So that's going to be my area that I'll use. And the pressure at that point, well, if this distance, remember, if you look at my coordinate system, it's fixed at the bottom. So this distance would be y. So since the whole thing is a height h, the distance from the top will be h minus y. Right? So my pressure acting on that surface will be rho g h minus y. That'll be the pressure at that point, because that's the depth from the free surface. So my little bit of pressure force will be the pressure times a little bit of area, and there's a negative sign there too. So it's going to be rho g h minus y, that's my pressure, and then the area is going to be a minus dy times w in the I hat direction. So that's my little bit of pressure force. Again, this is the pressure, and this is my minus dA. So the total pressure force, I'm going to integrate that up over the whole area of the surface. Now, since I'm doing things in terms of strips of area here, I just need to integrate over y, right? So to cover the whole area, so it'll be as y goes from 0 to h, and then I add up all those little bits of pressure force. So let me take some stuff outside the integral because there's some constants here. So there's our integral now. So now we have to actually do the integral on the right-hand side. It's a pretty straightforward integral to do. Let me go ahead and just write it out. So we're going to get, when we do the first integral, it'll be a h squared. Then the next one will give us a minus 1/2 h squared. So in the end, we're going to get a minus 1/2 rho g h squared times w acting in the I hat direction. So that is the net pressure force acting on the sidewall. It's a little more complicated than what we had on the bottom because the pressure varies, right? And if you look at this expression for a moment, well, first of all, you see there's a minus I hat, which just means that the pressure force is pushing in the minus x direction. So it's pushing into the wall just as we expect. But one of the things you'll see is if you look at this for a moment, this is actually the area, or really the volume of this triangle over in the picture. Let me highlight it in yellow. If I took the area of the triangle here, that would be 1/2 the base times the height. The base would be rho g h, and the height is h, so it'll be 1/2 rho g h squared, which is this part of the expression. I'm kind of highlighting it in yellow there. And then the W is in and out of the page, so it's the volume of that kind of triangular wedge. So the pressure force is actually related to our pressure profile picture. And that's true in general. So that's the pressure force on the side. We found it using this integration approach, breaking it up into little bits and then adding it up over the whole surface. And this is the approach I highly recommend you use for all of these kinds of problems. It'll work for any sort of geometry, whether it's at an incline or maybe it's a curved geometry. It'll just work all the time. It can be tedious, no doubt, and you have to do an integral, but it works. It always works. And you can see physically what's happening here. You're actually trying to take the pressure over a little bit of a surface and find the pressure force on that, and then adding up all the little bits of pressure force. You can actually, it's a more physical approach. All right. Now we found the resultant force, or the net pressure force acting on the surface. Now what we need to do is find where that pressure force is acting, right? So it's acting somewhere on that surface. We just don't know where yet. The way we find that is we balance moments on the surface. So what we want to do is we want to make sure that the moment caused by the distributed pressure force, that's going to generate some moment on the surface. We want to make sure that if we replace the distributed pressure force with a resultant force, we get the same moment. So let me redraw the picture here. Let me go down here. So here's our wall. And let me put the coordinate system back on there. So there's y, here's x. Z is coming out of the page. Remember, this height is h. And let me also sketch in the pressure profile. So let's take a look at a small piece of area right there again. And let me draw the little pressure force acting on it. Let's draw that in different color here. So there's our little bit of pressure force acting on that surface. And then pressure force, of course, is acting a distance y from the bottom, right? So that pressure force is going to create a moment about the origin, right? We have an r cross f kind of calculation here. So that little pressure force is going to create a little bit of moment about the origin. So let me write out what that expression looks like. So the moment, the little bit of moment about the origin, and this will be just in the z direction. So I'm not going to put the k-hat vector here. It's all just going to be in the z direction. That little bit of moment will be y times dfp. But the dfp we already calculated previously would be the pressure at that point, which will be rho gh minus y. So that's my little bit of pressure, times the area there, which would be dy times w. Remember, I'm not going to put the vectors in here. We know that the moment, just from the picture, is going to be acting in the positive z direction. So that's the little bit of moment about the origin for that little bit of pressure force. And of course, to get the total moment about the origin, I would add up all the little bits of moment as I go from 0 to h. And I can solve that integral, so I can bring the rho g w out. And I'll have hy minus y squared dy all integrated. So let's evaluate that. And then we can write one last time. So this will be 1/6 rho g w h cubed. So that's the moment caused by my distributed pressure force, right? Hopefully that all makes sense to you. Now let's replace the distributed pressure force by the resultant pressure force. So here's my picture for that. So it's the same geometry. This is still h. And let me put the coordinate system back in there. So here's y. Here's x. Now what I'm going to do is I'm going to put in the resultant force acting over the whole side. And let's say that the location of that resultant force is at what we call the center of pressure, CP. So CP is center of pressure. That's where that resultant force is going to act. That's what we're really trying to solve for, is to figure out where that center of pressure is located. So we want that to give us the same moment as the distributed pressure. So the moment caused by that, so the moment about the origin for the resultant pressure force would be, again, an R cross F calculation. So it'll be YCP times FP side. But we've solved for the resultant pressure force on the side right up here, right? So I'll just write it out in terms of its magnitude. I don't need to put in the minus I hat because we're not doing it in terms of a vector here. You could do it in terms of a vector. You could actually have the R cross F as vectors and find the moment as a vector. No problem here. But I just know that it's already going to be about the z-axis. So I'm taking a bit of a shortcut. So when we write this out, this will be 1/2 rho g h squared w. And we want this moment to be the same as this moment. What we're doing is we're replacing, the idea here is we're replacing the distributed pressure force with the resultant pressure force. We just want them to have the same moment. So we have to put the resultant pressure force in the right location. So when I set those two equal, we can go ahead and simplify it and solve for the resultant pressure, that we can solve for the center of pressure. Okay, so now we're setting them equal. You see that the rho g's cancel out, the w cancels out. There's an h squared that will cancel out. And then we'll end up getting YCP is equal to 1/3 h. So that's where our center of pressure is. That's where our resultant pressure force should act. So going back to the picture, this YCP should be 1/3 h. It's 1/3 up from the bottom. And actually that corresponds to, if you go back up to our distributed pressure, it actually corresponds to where the center of area is for the triangle. So if you look at the triangle, the center of area of that will be 1/3 up from the bottom. So that's, that's true in general. So that's how you would find where the center of pressure is. And of course you could do this in, let's say, the z direction. What you'd find there, actually it's very simple. From symmetry, it would be right along the center line of the side wall is where the z center of pressure would be. Okay, so that's how you do this kind of integration hydrostatic pressure force calculation. It works all the time. You can do it for any kind of curved surface, any kind of oriented surface. It always works. And you can find the resultant force as well as the center of pressure. Let me say one other thing about this kind of approach. You'll notice that all the pressures I did here were in terms of gauge pressures. I didn't use absolute pressure. So you might ask yourself, well, why did you do it that way? Well, I can show you graphically very easily why we do it in terms of gauge pressure. So let me look at the sidewall again. Let me this time put in, let's do it in terms of absolute pressure. So I'm just going to show the picture of what the pressure profile looks like. So if I do it in terms of absolute pressure, I'm just offset by an atmospheric pressure, right? So this little offset is P atmosphere. Let me try to draw that more clearly. So that was atmospheric pressure, and of course down here it'll be P atmosphere plus rho GH. Right, so that's what the pressure profile would look like in terms of atmospheric, in terms of absolute pressure. But keep in mind that if we're dealing with absolute pressure, there's actually an atmospheric pressure acting on the other side of the wall. So let me draw it over here. So here we have also atmospheric pressure. So this distance is also atmospheric pressure. Because we're doing absolute pressures, we have atmospheric pressure contributions on both sides of the wall. But if you look at that for a moment, this area here is just the height times the width times atmospheric pressure, and this is just the height times the width times atmospheric pressure. They just cancel one another out. So in the end, the only contribution you have to the net force acting on the wall is just this orange bit here, which is exactly what we dealt with when we were dealing with gauge pressures. So when you're calculating hydrostatic pressures, you can use absolute pressures if you want, but you don't have to. And it's really much easier to use gauge pressures instead. It just simplifies the calculation. And the reason for that is because you have absolute pressure contributions on one side of the wall as well as on the other side of the wall. So it's just easier to do it in terms of gauge pressure. Now there's another approach we could take to actually calculating what the pressure force is and the center of pressure on the wall. And for that kind of approach, it's a force balance on a fluid element technique. Let me show you an example where I do the integration technique and this kind of force balance technique, so you can see the two different ways of doing it. So in this particular example, I'm going to have a wall that's inclined. So here's my free surface, and now I'm going to have a wall that's tilted. There's the base. I'm going to say the height here is still h. And I'm going to put a coordinate system. Coordinate system here, so let's call that the x direction. I'm going to put y pointing downward here. And we'll say that the wall is tilted at some angle theta with respect to the horizontal. So just from the geometry here, if h is the height, then this distance will be, let's see, let me work that out. Tangent of theta will be h over that distance in the x direction. So it'll be h over tangent theta. Okay. So that's the geometry that we're going to deal with for this particular problem. Let me do the integration approach. Let me just find the resultant force on that surface. So to do the integration approach, what I'm going to do is I'm going to choose a little area here. Normal vector, of course, acts inward. I'm not going to do this in terms of vectors, just to keep it a little cleaner. My area there, oops, let me fix that. My area there will have both an x and a y contribution. So if I just draw this, this is a little bit that's a little bit dy, here's a little bit dx. Let me zoom in down here on that. So there's my area. Here's the dy. Here's the dx. Remember, this angle is theta. So my area is going to be, there's my normal vector. And this is theta also. So I'm going to have dy in the I hat direction, and it'll be dx in the minus j hat direction. Right? So when I look at this, let me erase that normal vector. If you look at the projected area for the dx, there's a normal vector kind of pointing upward in the minus y direction. Right? This projected area sort of has like its normal vector pointing upward, and whereas the dy has its normal vector projected horizontally in the positive I hat direction. So that's where our area vector comes from. There's a little bit in the y, in the I hat direction, which is that projected part with the normal vector pointing that way. Remember, a normal vector on the surface is like that. So we have a component in the x direction, and then we also have a component that's pointing in the minus y direction. Okay, so that's my little bit of surface area. The pressure on that part of the surface here will be rho g y, because y is the distance down to that little bit of area. Right, here's our y coordinate system, so it's just some depth y. So our pressure is rho gy. So our little bit of pressure force, is going to be the pressure, rho gy, times the area, which will be, and there's a minus sign in front of all this, so it'll be dy I hat minus dx j hat. The minus sign because remember the little bit of pressure force is minus PdA. So if I want the total pressure force, I have to integrate it as y goes from 0 to h. Okay. Now, before I do the integral, you'll notice that I have a dy and a dx. Since I'm going to integrate as y goes from 0 to h, I really should turn the x into a y. And I can do that just from the geometry here. If you look at that geometry, again, tangent of theta is dy over dx. So dx will be dy over tangent theta. So I can substitute that in. This will be minus dy over tangent theta. It's important if you're going to integrate over y that everything's in terms of y as much as possible. So we can go ahead and integrate that. The other thing I forgot to do here is this is all, I'm going to assume it's all per unit depth. Okay, so it's like a distance of 1 meter into the page, since I didn't put the depth here. Okay, so we can integrate this. So this will end up being, let me just work this out. Let's make sure I've got the math correct there. I think that's all correct. So our final pressure force will be minus 1/2 rho g h squared in the I hat direction plus a 1/2 rho g h squared over tangent theta in the j hat direction. So that'll be our resultant pressure force. So there's some component pushing in the minus I hat direction, so that makes sense. Here's x. So it's pushing to the right, which makes sense. And then we also have a component in the positive j hat direction, which is pushing down on the surface, which makes sense. That's in the positive y direction. So that's what our resultant pressure force would be using our integration approach. It's a little more tedious, as I mentioned before. It can be a little bit tougher because you have to be careful with those little areas. But this is what we get. And that, by the way, is all per unit depth. Now, the other way that you can solve this problem, and it's kind of a clever way, and it works equally well, but generally is best used for simpler geometries is to use a force balance approach on a fluid element. So what I mean by that is, let's say we have let's balance forces on a triangular piece of fluid that's adjacent to the wall. Okay, we're going to balance forces on that little piece of fluid and then see what kind of pressure force we get for that. So let me draw the forces, a free body diagram acting on that piece of fluid. So on the left-hand side, we have a pressure distribution, right? And we already know what that resultant pressure force would be. It's going to be a 1/2 rho g h squared, because we've done that one before. We also have the weight of the piece of fluid. Remember, we're doing a free body diagram on the piece of fluid. And then we also have a force, the pressure, or the force that the wall exerts on the fluid. I'll just draw it in some arbitrary direction. I'm trying to solve for what the force is that the wall exerts on the fluid. That's what I'm going to try to solve for here. So let me just draw the resultant pressure force here. We said it was 1/2 rho g h squared. I'm doing this all per unit depth. Okay. The weight of that triangular piece of fluid will be the density times gravity times the area. Again, I'm doing it per unit depth. The area will be 1/2 the base times the height. 1/2 the base, this will be h over tan theta times the height, h. The base part is this distance here, h over tan theta, that I worked before. So the area of that triangle is 1/2 the base times the height. So that's the weight. Now if I sum the forces and set it equal to 0, just doing a force balance on that triangular piece of fluid, in the x direction I'll have a minus 1/2 rho g h squared I hat. That's this force, resultant force here, that's in the minus x direction. Then we have the weight in the y direction. So that's in the positive y direction. So that'll be a 1/2 rho g h squared over tangent theta, j hat. And then we have this force that the wall exerts on the fluid, and I've just drawn it just some arbitrary direction, F, W on F. And again, I'm doing things in terms of gauge pressure, so I don't have to worry about any sort of pressure force on the top surface of the triangular element. So if I solve for the force that the wall exerts on the fluid, I'm going to get this. Oh, that should be a positive because I moved it to the other side. So that's the force the wall exerts on the fluid. And we know from Newton's third law that the force that the fluid exerts on the wall will be equal and opposite. So the force that the fluid exerts on the wall will be minus the force the wall exerts on the fluid. So it'll be a minus 1/2 rho g h squared I hat plus 1/2 rho g h squared over tan theta j hat. So that is the force that the fluid exerts on the wall. That's our resultant pressure force on the wall. And if you look at that, that's exactly the same result that we have up here. So that's just an alternate way of doing the problem. So you can either use the integration approach, which works all the time, but can be a little tedious, no doubt about it. Or you can, if the geometry is convenient, you can balance forces on a fluid element and find the resultant force that way. Now, if you wanted to find the center of pressure, with the integration approach, you can replace the distributed moment caused by the distributed pressure with the moment caused by the resultant pressure force. Do that, integration approach that we did previously. Again, that'll work every time. You can also do it here with this triangular piece of fluid approach. You just need to know where the center of mass is for your little triangular piece of fluid, like in this particular case, to make sure you get the moments balanced. So you're just trying to find balanced moments using this approach as well. So you can do it both ways, and I think both ways are equally fine, although I tend to lean toward the integration approach. There is a third way you can go about solving these problems, and this is the technique that's shown in a lot of textbooks. It's based on kind of a formula approach. These textbooks will do a derivation. They'll give you some formulas, and then you look up moments of inertia of whatever shapes you're dealing with in a table, and you can plug and chug into the formulas. I don't like that approach. It works, but I don't like it. And the reason is because it does have this kind of plug and chug feel to it. It takes you away from the real physics of the problem and gets you into this kind of which is the right formula do I need to use. You also need to have a table of moments of inertia, or at least some access to it, through the internet. I just don't like that approach. It's fine, it works. Some people do like it, but for me personally, I just think it's a kind of a plug and chug approach, and I'd rather see the physics and kind of understand it better. The other nice thing about the integration approach is it lends itself well to computer programming. So you can imagine if you had a CAD file of some shape that you wanted to find the net pressure force on in the center of pressure, you could discretize that shape into a bunch of little triangles or a bunch of little areas, and then find the little bit of pressure force on each one of those areas numerically, just pressure times the area for that little triangle, take into account the orientation of the pressure force, and then just add it up numerically. So I think that integration approach lends itself well to computational implementation. The moment of inertia approach really doesn't do it that well. It can't handle arbitrary shapes as easily. So anyway, I like that integration approach, and I highly recommend you do it. In fact, all the examples I do in separate videos will use that integration approach.